Hello, everyone. Today we are going to introduce what blockchain technology is and how it works. You may have recently heard about blockchain, cryptocurrencies, or other types of distributed or decentralized ledger technologies which are addressing modern problems, such as the speed and ease of international currency transactions. And yes, blockchain is related to cryptocurrency, but it is not cryptocurrency. Blockchain is a technology that enables a distributed ledger to be shared across a peer-to-peer network. As the name suggests, blockchain is a chain of data blocks stored on hundreds or thousands of computers or servers distributed over a wide geographical area. It is a complete ledger which maintains a copy of all the credit and debit transactions of a digital asset. That digital asset can be a representation of something physical, such as a pen or a chair, or digital, such as a virtual currency or data. Essentially, whatever can be represented as a number can be treated as a digital asset. Blockchain is a decentralized ledger tracking one or more digital assets on a peer-to-peer network. When we say peer-to-peer network, it means a peer-to-peer decentralized network, where all the computers are connected in some way, and where each maintains a complete copy of the ledger. The ledger can also be seen as a bank account statement since day zero. Let's say you open an account on 1st Jan 2017. Then the ledger will keep track of every transaction in and out of your account from that day. So, if you create a balance statement from day zero, it can be called a complete ledger. Just imagine now that the full ledger or bank account statement is copied to thousands of machines at the same time in such a way that each machine can verify the individual transactions without involving other machines and announce whether it's a valid transaction or not. So, now the question is, how does the blockchain come into the picture, and how is it related and connected? In a traditional physical ledger, in the form of a book, each page contains the information as lines on pages. You can imagine a book as a kind of rudimentary blockchain, where the pages represent blocks and each page is connected to every other page through a page number. In a book, all pages are in a particular order. That's why if someone tampers with a specific page or removes any page, it is obvious, since the pages are numbered and are connected to each other in a particular order. If you can imagine a blockchain as a book, with each block or page connected to every other one, then you understand the essential characteristic of blockchains already. Blockchains are ledgers which record every credit and debit transaction in such a way that the details cannot be altered by anyone without others noticing, because each block is connected to every previous block. To explain the book analogy simply, the book represents the blockchain, the page represents the block, and each entry on each page of the book represents a blockchain transaction. As I have mentioned already, it's easy to detect if a page has been removed or deleted, and it is also easy to arrange the pages or the blocks in order and then identify any suspicious activity. That's why the page numbers are significant in a legal agreement or in an MOU, because it helps the readers to understand if there is a page missing in the entire agreement. It is obvious that changing or removing a page can change the meaning of the whole agreement, and this is very important in a ledger as well. Removal of a page in a ledger can corrupt the entire ledger very easily. If you have an account statement that has 100 pages, and if someone removes page 65, then you can quickly identify this because the record will not be complete. Now, you might be wondering how this relates to cryptocurrencies. In fact, cryptocurrencies are nothing but digital tokens defined as numbers in the blockchain, which are tracked from day zero. Take Bitcoins, for example. They are just numbers which are stored in a blockchain ledger and which have been tracked since day zero. People need that digital number because there can only be one copy of it, which reflects the fundamental nature of the currency. If I have 100 Bitcoins and you have 0, and I transfer 50 Bitcoins to you, then I no longer have 100 coins, because the ledger will update, and it will remove 50 coins from my balance, and add 50 coins to your balance, creating a single, secure copy. Because people desire to purchase and own Bitcoin, it has assumed real-world value. In reality, though, it is just a number stored on the blockchain. So, this is how a block looks. The genesis block is called the day zero block, or block 0. It is the block that will contain the starting balance, which can even be 0. If a blockchain is not minting new tokens or new balances every single block, then the Genesis block must have an initial balance. Otherwise, there would be no way to introduce the new balance. As you can see in the Genesis block, there is something called a nonce, which is a small string-based number. Here, sign N1 represents the signature of the previous block. Since this is a Genesis block, we are keeping the signature of N1 at 0. Imagine that A's balance is 10 tokens, B's balance is also 10, C's balance is 15, D's is 5, and E's is 20. In this block, there are 3 transactions that are initiated where A transfers 1 coin to B, B transfers 3 coins to E, and E transfers 6 coins to D. As you know, these transactions have happened. The new block must accurately reflect the new balances, in line with these transactions. A new block is then added to the blockchain, and you will notice that there is a sign N, which is the signature of this whole current block. As you can see, this signature of the block number 0, or sign N, is being generated by the digest of the full block. This is the signature of the full block, which is being calculated by SHA-256 of the current block. SHA-256 is a simple hash algorithm, which is a crunch of any length of data into a unique string of a fixed length. This way, if any single digit or letter has been tampered with in this block, the signature will completely change. It is not possible to reverse the digest or signature to the original input data or original data. This is always one-way crunching. So this way, the SHA-256 has crunched the entire block into a unique, fixed-length string, and we call it the signature of the block. Next, if the new block has been added, the signature of the previous block will go to the sign N1 into the new block as a header. The nonce will thus be created. This nonce will be guessed by a miner, who can be a person, computer, or server, or the process which is confirming the block. The miner will figure out this number and will update the balances of all the addresses. So, let's say A now has 9 tokens since A transferred 1 to B. B has transferred 3, but you know B has also received 1, so B has 8 tokens now. Similarly, C, D, and E, and there are only 2 transactions which are new. So, now the transactions may be affecting the balance of the inputs and are creating the output which will go here. Here, the sign N1 is the signature of the previous block which goes here, and again the signature of the whole new block is created through this process which will again go back to the next block as a header. Here, the nonce is the number which is being generated by the miners. These numbers, or the nonce, should be generated in a particular way, through the mining algorithms. It depends on each particular blockchain, but in a general sense, the nonce should be generated in such a way that it's truly random and directly proportional to the difficulty of the blockchain. Building a block and adding it into the blockchain is a task of miners. Miners solve for the nonce in such a way that the new block's signature is in a particular order. Technically, the miner has to try millions or billions of times before arriving at the right number, and that is why the process is called proof of work, POW. Solving for the nonce involves considerable computation power and effort by the miner. The whole process generates proof that the particular block has been verified and added to the blockchain. In turn, miners are rewarded for their work with coins or tokens. This reward and the difficulty of solving for the nonce creates a competition among the miners to be the first to solve it. This competition adds to the difficulty of corrupting the blockchain in any way, because every miner verifies every other miner's work, and every miner wants to receive the rewards. Since the newly minted coins have value, the miners are satisfied. Moreover, the entire blockchain continues to function smoothly because a new block has been validated and added. In this way, as more blocks are added, blockchains can grow to lengths of hundreds of thousands or even millions of blocks, depending on the algorithm and the technology used, which determine how frequently blocks are being added. For example, on the Bitcoin blockchain, the average time of adding a new block is 10 minutes, while on the Ethereum blockchain, adding a new block to the blockchain takes just 15 seconds. Because blockchains become so long, and because each block is linked to the one preceding it and the one following it, it becomes very difficult for hackers to modify data on the blockchain. If, for example, a hacker wanted to modify block number 50,000 because it would be beneficial for him in some way, he would also need to modify all the preceding and following blocks as well. And this would be almost impossibly costly and time-consuming to do. Alternatively, by solely modifying the data in block number 50,000, the hacker would in effect be creating an offshoot chain of the main blockchain. And this offshoot would be rejected by the blockchain miners and community, who always follow the longest chain. This is how blockchains are kept secure. As we have stated, each block in the blockchain is built on top of the block immediately preceding it. Thus, it is very difficult to tamper with one block without affecting the blocks it connects to. Overall, it is a very difficult task to modify any part of a blockchain without someone noticing it. An alternative option to POW is proof of stake, POS, where miners develop a reputation based either upon the number of coins or tokens they own, or their status in the market. The higher their reputation, the more easily they can add new blocks to the blockchain. Private blockchains can choose other methods for adding blocks. They can even trust miners by using legal agreements or contracts. This is another interesting way to choose miners, and it is another example of proof of stake. So now we will create our definition. Let's not follow some XYZ definition which you will probably not remember easily. Since we now understand the essential logic behind blockchains, let's create our definition. Blockchains are decentralized databases which store information in the form of transactions. They can be public or private. They store data in an immutable way, and by immutable we mean that it is very difficult to tamper with the data and very easy to detect if someone has done so. It doesn't mean that data will never be tampered with by anyone. Data tampering is possible on the blockchain, but it will only affect the hacker's local copy. And if you are not able to change the entire blockchain or the entire network, then it is pointless. Because of this, blockchains are incredibly secure. Data is validated and entered into the blockchain via consensus-based algorithms, such as a POW or POS, where consensus is required before adding a new block or adding new transactions. This helps secure the entire blockchain without involving any trusted third party or regulator. Blockchains use cryptography, and they operate over peer-to-peer networks. So here's our definition. Blockchain is a consensus-based, secure, decentralized, public-private database which stores information immutably over a peer-to-peer network. So that's our definition. Pretty simple, right? Let's summarize what a blockchain is. It is a decentralized distributed ledger, a data structure where data is being stored inside blocks in the form of transactions. It removes any dependency on a trusted third party for recording the data on the blockchain, since people are incentivized to compete with each other to add each new block and to maintain the blockchain's integrity. On public blockchains, more complex algorithms are required to avoid malicious activities. As each block is built on top of the previous block, immutability is achieved. Again, immutability here means that it is very difficult to fake or alter a block and very easy to detect any tampering with the blockchain. As every participant on the blockchain contains an almost identical copy of the blockchain ledger, only the last few blocks might be different based on the geographical location and the communication protocol. But the ultimate ledger is always the same. Okay guys, so that's all you need to know about blockchains. If you want to check out more information on other certifications, then please go to our website at blockchain-council.org, where you can find more courses. Thank you.